Hello everyone, welcome to our presentation of Pik-Fix, Restoring and Colorizing Old Photos Accepted to WACV 2023. This paper is collaborated between UCLA, UT Austin, Cornell University, Northwestern University, Cleveland State University, and Pik-Fix Technology. Old photos contain our memories, but they become faded and broken as time passes. Fixing and colorizing these legacy photos can make our memories more vivid. However, repairing these photos is often costly. So it is important to study the problem of how to use deep learning to automatically fix your old photos. Existing works either focus on old photo restoration without any colorization, or only colorization but without handling other restorations in legacy photos. So in order to comprehensively enhance the quality of old photos, we propose a joint colorization and restoration framework called Pik-Fix. This is the first end-to-end solution that can handle both degraded colors and mixed degradations. To ameliorate the difficulties of blind colorization, we use a reference-based approach to guide the colorization process. Our method is only trained on synthetic dataset and it can generalize well to realistic dataset. We've also created a first-of-its-kind real old photo dataset containing 200 images of real old photos with their corresponding ground truth, created by Photoshop experts. The whole Pik-Fix model contains 3 subnets. Subnet 1 is a multi-scale restoration net that takes the grayscale input and predicts the restored grayscale output. We use L1 loss and perceptual loss to train this restoration net. We then feed the restored grayscale input into the colorization unit to predict the chroma components in lab color space. We use L1 reconstruction loss and adversarial loss to train this subnet. To help the colorization learn easier, we provide a guidance image R_L that will provide a color components as additional information to the colorization net. Note that before blending the colors, we will match the similarity of these 2 grayscale images and warp the color maps of the reference. The whole system is trained end-to-end using the weighted sum of all the losses. Note that we also add an earth-moving distance loss between prediction and reference chroma channels to enforce the color histograms are consistent. We use pure synthetic data to train Pik-Fix. We simulate unstructured degradation including random noise, Gaussian blur, JPEG, and convert it to gray image. We also add the scratch, crack, and dust patterns to the image to simulate real old photos. Here are some examples of our synthesized training images. To select suitable reference images, we use the perceptual distance in the VGG feature space as metric and search in the training set. During testing, users can either upload their own or use our suggested one. Here we show the visual results of Pik-Fix on colorization only. With a properly retrieved reference picture, our model can generate vivid colorization results as compared to existing models. Here Table 1 shows the quantitative results without and with degradation, which demonstrates the great performance of our method. In order to demonstrate the results on realistic old photos, we create the real old dataset containing 200 images. Each image is repaired and calibrated by Photoshop experts. Our model trained only on synthetic dataset is able to deliver superior performance on real old dataset among the compared models. Here we show some qualitative comparisons on the real old dataset, where our method demonstrate better restoration and colorization results compared to previous methods. In conclusion, we build Pik-Fix, a framework that can comprehensively enhance old photos. We also create real old dataset that contains 200 pairs of real old photos, each having repaired and calibrated ground truth. Our extensive experiments demonstrate that Pik-Fix shows greater performance on both synthetic and realistic benchmarks.